In this video, I'm going to give a brief overview of what is called consistent quantum theory, or sometimes consistent histories quantum theory, or it usually has the word quantum theory and consistent in it. And so that's what we will be talking about here. And so this is an interpretation that is mostly thought up by this guy, Robert Griffiths, not to be confused with David Griffiths, whose textbook I used for my quantum mechanics playlist where I was, doing all the calculations and things like that. And so he boasts that this is Copenhagen done right. Essentially, what he means by that is that he's going to sort of formalize the Copenhagen interpretation. And so when somebody formalizes something, essentially what they're doing is taking something that's somewhat easy to explain and making it more difficult to explain. So that's kind of, what formalizing something means. But it's important because it, makes something more consistent, which using that word in a different sense than what it's meant here, but and it makes it something that you can actually make predictions with and things like that rather than just sort of describing something in words. And so I'm going to kind of go through this somewhat quickly here. And so if what I'm talking about at first seems somewhat obscure, when I get later in the video, I'm probably going to explain a little more, but I want to sort of talk about some of the, I guess, motivation for this way of looking at quantum mechanics. And I will have the show notes or the lecture notes, I guess, in the description down below, and that will also contain my references, so you can check that out if you want to learn more about this. But it is very similar to the Copenhagen interpretation, especially in the sense that it takes Bohr's complementarity idea very seriously. And that's probably kind of the big thing that consistent quantum theory does, is sort of take that complementarity that Bohr was always talking about very seriously, and essentially says, kind of getting ahead of ourselves a little bit here, that when you measure something in one way, so, the complementarity thing says that there can be two different things that are not compatible with each other. So we could think of the spin in the z direction, so we can have spin up or spin down, or the spin in the x direction, so that's, maybe spin left and spin right. And so the complementarity thing says that if we are measuring in this frame here, so in the z direction, then we can't really say anything meaningful about the x direction. And so consistent quantum theory is essentially going to say that when we measure something in the z direction here, so in the z direction, we are finding out something real about the system, but then this thing in the x direction is in a very, I guess, in a very real sense, it's not real in a way. And so anyway, we'll get into that here in a little bit. And so like I said, I'm going to sort of just go through some things I have highlighted here at first. If you want to read more about this, you can check out the lecture notes, but I just want to hit sort of the important points here. And so I'm going to be borrowing from this paper a lot, so the Pierre Hohenberg 2010, and I'm actually going to be borrowing a lot from Griffith's book that he released in, I believe, 2002. And so those are going to be the things that I'm going to use as my references here. And so the thing I wanted to point out here, so this is Hohenberg from the 2010 paper. So he wants to say that their formulation of quantum mechanics is based on these assumptions, where the first two are somewhat standard, I guess, but it's C here that is kind of important here for our purposes. And so it's saying that the principle of unicity does not hold. And so unicity is essentially what I was talking about in a previous video. So that was this right here, the John Stuart's Bell formulation of causality, where Bell had this thing here where we have this slice of space-time, and so that can be sort of completely described. And so here in the book I was using for this, they were using this uppercase sigma here, which is a sort of complete description of everything in that slice of space-time. And so that is what unicity is that it's possible to have a complete description, a single description of everything that is true in that slice of space-time. And so what consistent quantum theory is saying is that this principle of unicity does not hold, that there is not a unique, exhaustive description of a physical system or process. Instead, reality is such that it can be described in various alternative, incompatible ways using descriptions called frameworks, which cannot be compared or combined. So that's what I was saying up here, where with the z and the x right here, where if you are looking at it in one what they call framework, then the other framework is in, like I said, a very real sense, not real. And so they cannot be compared or combined. This is the principle of complementarity or incompatibility expressed in terms of the single framework rule to be elucidated in what follows. And so, like I said, that's kind of the main thrust here. But then the consistent quantum theory, they try to show how using this sort of way of looking at it can explain some of the strange behavior of quantum mechanics. And as we'll see, I think that it's somewhat of a unsatisfactory way of trying to sort of explain these, weird phenomena in quantum mechanics. But they're saying in consistent quantum theory that that's, what they're going to try to do here. All right, so like I said, we can have the framework of, say, spin in the y direction. So here I'm using y instead of z. And the framework and the spin in the x direction. This should actually be an x right here, not a y. So that should be an x right there. But since the operators do not commute, so we would get non-zero from trying to commute these, we cannot compare the two frameworks. And so that's kind of the main way of seeing that we have incompatible frameworks, is that if their operators do not commute. And so that would be, things like position and momentum in the Heisenberg uncertainty principle, but also spin states, like either if we're looking at it in the z direction, the x direction, or the y direction, those do not commute, and so those are incompatible frameworks. All right, so we can go down here. So this is still going from this Pierre Hohenberg paper here. So he says the Einstein, Podolsky, Rosen paper argument starts from two basic assumptions. So there's EPR1, so they're splitting this up into two basic assumptions. So that's a classical reality criterion according to which a physical quantity is real if its value can be predicted with certainty without in any way disturbing the system, and a criterion of separability or locality, which was articulated more clearly in subsequent presentations, according to which the real factual situation of a system is independent of what is done with another system if the latter is spatially separated from the former. And so he says that in CQT, or consistent quantum theory, modifies EPR1 by replacing this classical realism assumption by quantum realism, whereby physical properties of a system are real relative to a well-defined framework, but properties belonging to incompatible frameworks are not simultaneously real. And so that's what I would mean by saying that, if you measure the spin in the z direction, then its spin in the x direction is not real. And so that's essentially what they're saying, is that these complementary sort of things, so the complementarity in Bohr's use of the word, or incompatible in the consistent quantum theory terminology, are not real. And so that's we'll see that they're going to try to say that because they're not real, that's why we see these weird quantum phenomena. And so in light of Bell's inequality, instead of rejecting locality, consistent quantum theory rejects classical realism. And so they're saying that instead of rejecting this they're going to reject this, where they're arguing that it's the EPR2 assumption up here that usually gets rejected in interpretations of quantum mechanics, that we say that locality must not be something real. But here they're saying that they're going to modify what we mean by realism. And so, indeed, starting from the two EPR assumptions, Bell was able to derive what is known as the Bell inequality, which is violated by quantum correlations. If one believes quantum mechanics, one is thus forced to reject either classical realism, locality, or both. A number of authors, including Bell himself, and many philosophers and commentators favor rejecting locality, but consistent quantum theory most definitely opts for retaining locality and rejecting classical realism, since the latter violates the single framework rule. Where the single framework rule, remember, is that thing that's saying that we can only say, when we make a measurement, say in the z direction, we can only say something meaningful about that because that is a framework that is incompatible with the sort of x direction framework. And so they are saying that, if we want to say something real about both the z and x direction at the same time, that violates the single framework rule, because we can only use one framework when trying to describe it. All right, so going down here, so in particular the existence of lambda, where here lambda is what is used for the sort of complete description of the system here at some point in the past, where in my other video we were using this uppercase sigma here. And so here they're using lambda, so I kind of replaced that with lambda here. So in particular, the existence of lambda variables in this equation up here they're talking about that fully specify the state of a physical system depends essentially on some assumption additional to locality, which has been variously named predictive completeness, or classical or weak realism, or counterfactual definiteness, as well as other designations. According to these authors, so they're saying, according to the proponents of consistent quantum theory, it is this additional assumption that is contradicted by quantum mechanics. And so they're saying that it's the assumption that we can have a complete and full unitary description of everything at that time, where when in consistent quantum theory they're saying we can only have a description given a single framework. So within a single framework we can have a description, but then we would be lacking any description in other frameworks. And so it is this additional assumption that is contradicted by quantum mechanics, and referring to the above equation simply as a locality assumption is at best misleading. Indeed, the violation of the above equation by quantum mechanics is due to the incompatibility between different local choices for measurement type. So measurement type A, so for instance S sub x of A, or in the x direction or in the z direction, or different choices for b, rather than any spooky action spooky interaction between the distant spins s sub a and s sub b, which we are sort of measuring here and here far away from each other. And so this is unrelated to locality. It has to do with having the different frameworks. And as we'll see later in this video, in a given framework, they are taking a very realist position. And so meaning that, so in the usual sort of spooky action at a distance quantum entanglement thing, what they're saying is that if at s sub a we measure in the z direction and we get spin up, then we know instantly that at s sub b here, that if they measured in the same direction they would get spin down here. And so we are saying that that we are gaining instantaneous information here about what they would see over here, regardless of how far away it is. But what we'll see here is that in the consistent quantum theory, they're saying that when, sometime in the past we entangle these particles, that one of them really does take a spin up. And so it was spin up even before it was measured at S sub A here. And so this one was definitely spin down at S sub B here. And that is real as long as we are measuring in the Z direction. But it would be not real if we instead measured in the X direction. And so they're saying that these weird spooky interactions between the distant spins are not because of some action at a distance, but because of this non-reality of frameworks that are not used in our measurements. And so I made this table down here to sort of look at the different possible outcomes of measurements. And so like the first one here, we're measuring both at the A position here and the B position here in one direction. So that's what the sub A here is telling us. And so if we get this at S sub A, then we also get the measurement at S sub B that we would predict given what we saw in S sub A. Then in the bottom one here, they're both measuring in the same B direction. So if S sub A gets B, then we know that S sub B also gets B. But then we have here that if we measure in the A direction with A at the S sub A here, then the S sub B could get either A or B. And same as if we had S sub A measure in the B direction, then S sub B could get the B or A direction here. But anyway, so in particular, Griffiths, so he's talking about Robert Griffiths here, argues that there are no quantum variables lambda that satisfy equation 11. In other words, there is no complete description of the universe at some, time slice in the past. There are no quantum variables lambda that satisfy this if the different choices for A or B do not commute. What is at issue here is not the fact that this equation above and the Bell inequality that follows from it are violated by quantum mechanics. The issue is to understand the origin of the violation and whether it is associated with a failure of realism or completeness or of separability. Needless to say, there is no consistent framework for which the equation above is satisfied. The equation above being full description of reality at some time slice into account. And so they're essentially saying that there is no full and complete description of all the, possible states of things in some time slice in the past. So in other words, measurements of a type A are working with a different frameworks than measurements of type B. And so, for instance, this measuring A at position A in the A direction and measuring at position B in the B direction is incoherent. And again, what I mean by that is, if at some point in space we're measuring in the Z direction, so up and down, and then at some other point in space we're measuring in, say, the X direction, so left and right, then there is nothing we can coherently say about, the system at these two different places, or even the same system at two different times, as we will see here in a little bit. So say we have some particle and we measure it in the Z direction right here, then at some later time we measure it in the X direction here. It wouldn't make any sense to say that, that because we measured it in Z, say up right here, that then when we measured it in X right here, that it is still in the, Z up direction. So there's nothing meaningful we can say about the Z direction when we measure in the X direction, since they are describing incompatible frameworks here. So now we can get into sort of what they mean by these histories here. So this, like I said, is sometimes called the consistent histories interpretation of quantum mechanics. And so what we mean by that is a family of histories satisfying the above two equations. So this one right here, meaning that all of the probabilities add up to 1. So it's, exhaustive, and that they are mutually orthogonal, so that they are, sort of mutually exclusive from each other. So a family of histories satisfying the above two equations is called a consistent framework, or just a framework for short, because this right here ensures that the framework is exhaustive, as I said, and this one right here implies that the different histories are exclusive, so they do not interfere with each other, thus permitting an interpretation in terms of standard Boolean probabilities within each framework, meaning that one history is true and all the other ones are false essentially. So a hallmark of a quantum system as opposed to a classical system is the existence of more than one framework. So again, it's one of those things where if we can have a framework for the z up and down direction, but we can also have a framework for the x direction, or for the y direction here. And so there are multiple frameworks in which we can think of the spin of a particle, for instance. So any statement about a quantum system is expressed in the form here of this probability. And so they're saying that the probability of a particular history is going to be, some number between 0 and 1 here. And so what they're saying is the probability of the kth history of the framework, so this f here of these different possible histories here, is some number here between 0 and 1. Such statements refer to real histories, which consist of sequences of real properties represented by projection operators onto states of the system. So the reality of these properties, however, is relative to a particular framework. And so I'm trying to illustrate this here, where we have at different times here, so time 1, time 2, time 3, all the way up to time n here, we can have, say, this state of the system here at time t2, or we could have this state, or this state, or this state. And each of these rows represents a particular history here. And so these are, the different histories that we have here in this family of histories. So we could have this, alpha 1 right here, which would be sort of this one down here, and that would sort of go over this entire thing right here. So we could have this as one of our histories, or we could have this one as one of our histories, and so on and so forth. And so one of these histories is actually going to be real. And so when we take a measurement, what we'll see is that, we could get a particular, so we take a measurement, say, at time right here, and so then we would know that the system, had we measured it at this time, would have had that state there. So each framework gives the history of possible states at each moment in time. For instance, if you take a measurement at time t sub n and you obtain this, then that means that the history of that system was our alpha 2 here. And so that's kind of what I was saying here, where, say, we took a measurement at this point right here, and we got this state right here, then we would have known that at time 2 that this was the state of the system at that earlier time. And so, this is the thing that quantum mechanics usually, I guess what they sometimes call the orthodox interpretation, sort of rejects, is that the system didn't have a particular state at an earlier time than the measurement. The wave function collapsed into a particular state when you took the measurement, but consistent quantum theory is saying that no, in fact, the system did have that actual state at an earlier time, so we can actually know what the state of the system was even when we were not measuring it. And so that's what they mean by quantum realism, that there's this realism of the state in that framework at an earlier time. Whereas, if you take the measurement, say, in the z direction at this time, then we know what the state of the system was in the z direction at an earlier time, but we wouldn't then know what the state of the system at in the x direction was at an earlier time. And so in a very real sense, as I keep saying, it was not real, that there was no real description in the x direction at that earlier time. So yeah, where each framework gives a history of the possible states at each moment in time. So like I said, if we take a measurement at t sub n and obtain this, then that means the history of this system was this, where these are the tensor products. But you can just think of it as each moment in time, as these different points in time right here. So such that had someone taken a measurement at say T3, they would have obtained this right here. So again, saying that in a particular framework, that the measurement at some time would tell you what the state of the system really was in that framework at an earlier time. But then we could have another consistent framework here. So I'm using beta for this one, but we cannot say anything coherent about this framework here and this framework here at any t sub j. So at any time along one of these histories here. So in other words, obtaining this state at time t sub n would not tell us anything about this state at time t sub n for any of these. So it would not tell us what history was actually real in the other framework for that. So this is the case if these do not commute. So if the operators for these two incompatible frameworks do not commute, then this is true of those. But any two frameworks that do commute can have consistent histories. So if we look at our example with the spin in the z direction, then our consistent histories would be, so we would have the spin up in the z direction or spin down in the z direction, such that these are sort of mutually exhaustive and mutually mutually inclusive here. So where, for instance, obtaining a measurement at time t sub n would give the probability of z in the spin up state as 1/2, and the probability of getting spin up or spin down is the probability of spin up plus the probability of spin down, so it's 1. So these are mutually exhaustive, and the probability of spin up and spin down is 0. And so that is where we take the probability of one plus the probability of the other and subtract the sum of them, and so that gives us 0. So now if we also measure spin in the x direction, we likewise have that. We could have spin up in the x direction as 1/2, and the probability of this is sort of mutually exclusive, or mutually exhaustive rather, and mutually exclusive here. I think I might have said mutually inclusive above, but I meant exclusive. And so we're saying that all of the possibilities add up to a probability of 1, and that the probability of getting both at the same time is 0. And so they are exhaustive and exclusive alternatives. So exhaustive in terms of or, and exclusive in terms of and. So all of the probability of up or the probability of down add up to 1. The probability of up and the probability of down at the same time add up are 0, that you can't get both at the same time. But if we ask what the probability of getting spin up in the z direction or spin down in the x direction, the question is meaningless. And so the word meaningless here is important because it is not saying that the question is correct or incorrect, but that it has no meaning. And so we can see here we have a complete description in one framework, or we can have a complete description here in the other framework, but we can't have a complete description of both of them. So of particular importance is the fact that consistent histories abandons a principle here called unicity, which is deeply embedded in both conventional and scientific thought and is taken for granted in classical physics. It is the idea that at any instant of time there is precisely one exact description of the state of the world which is true. If the consistent histories understanding is correct, quantum mechanics has made unicity obsolete in somewhat the same way as modern astronomy has replaced an unmovable Earth at the center of the universe with our current understanding of the solar system, and ignoring this feature of quantum world is what has given rise to so many conceptual difficulties. And so this is actually from a paper that Griffiths put out where he was sort of trying to respond to some critics of his consistent quantum theory. All right, so this, what I'm going to talk about now is essentially saying the same thing that I've been talking about before, but this is actually the treatment that Griffiths gives in his book on the subject, his 2002 book here. So, like I said, I'm going to be essentially saying the same thing, but in maybe a slightly different way to hopefully make what I'm talking about more clear here. And so, uh, Griffiths is talking about this Stern-Gerlach experiment here, where we can have our particle go through a magnet. So this is an inhomogeneous magnetic field that is going through here, and so we can get either spin down or spin up detected here. And so we have these two possible histories where at the position omega right here, we can have either spin up or spin down. At omega prime here, we can still have either spin up or spin down. And then when we get out of the magnet here, we can have spin up or spin down. But now what we see is that we have position up and position down. So if it's spin up, then we will see our result will show that the particle has gone to, sort of the position up right here, and this one has it going to the down position right here. And so it's sort of mutually exclusive which one we get. We can't get both the up position and down position, so the inner product of that is 0. And if the particle is prepared in the up state, in the x direction state, we get this superposition here in the z up and z down. So giving us a history starting from the initial state, psi sub naught here. So we have z in the up position. Well, this would actually be x in the up position right here. So we're preparing it in the x up position, and so we end up with this right here, which is a superposition in the x or in the z up and z down. And so this is saying that we also have a superposition of detecting it in our sort of upper detector or our lower detector. And so this is sort of that measurement problem in quantum mechanics of, how come we don't see superpositions in our measurements here when if we prepare this in the x up direction here, then we get a superposition of z up and z down. So how come we don't see a superposition in the up and down position of our detectors? And so Griffith says the unitary history in this above history right here cannot be used to describe the measuring process because the measurement outcomes, so in the up position or down position, are clearly incompatible with the final state in this above right here. So a quantum mechanical description of a measurement with particular outcomes must obviously employ a framework in which these outcomes are represented by appropriate projectors, as in the consistent family whose support consists of the two histories. And so we have these two possible histories here, so we could have it in the up or in the down right here. So Griffiths continues, the notation here indicates that the two histories are identical at times t sub naught, which would be this one right here, and t sub 1, which would be that one right there, but contain different values at t sub 2, so that would be that one right there. While this family contains the measurement outcomes of the particle going up or down, it is still not satisfactory for discussing the process in the above figure. So the figure I'm talking about is this one here. So we're talking about that Stern-Gerlach experiment there. It is still not satisfactory for discussing the process in this figure as a measurement because it does not allow us to relate these outcomes to the spin states of the particle before the measurement took place. So since the properties, so spin up and spin down in the z direction, are incompatible with a spin state in the x plus direction at time t sub 1, the different histories do not allow us to say anything about the s sub z before the particle enters the magnetic field gradient. It is true that the spin in the z direction at t sub 2 is correlated with the measurement outcome if we use the different histories, but this would also be true if the apparatus has somehow produced a particle in a certain spin state without any reference to its previous properties, and calling that a measurement would be rather odd. So a more satisfactory description of the process in this Stern-Gerlach experiment figure as a measurement is obtained by using an alternative consistent family whose support is these two histories. So the above histories have positive weights. We see that we get this right here. So if we have been up at time 1, given that we are in position 2 at time 1 is equal to 1. And so the probability of spin down at time 1, given that we are in spin down at position 2, is equal to 1, which is that essentially that quantum realism picture I was talking about, where we're saying that we see that the particle went to the, I guess, upper detector here in our Stern-Gerlach experiment. So we know that at the earlier time it was in the spin up. And similarly, given that we get the detection in the down detector, we knew that the particle was in the spin down at some earlier time. And similarly, if we know that the particle was in the spin up at an earlier time, then we know that we will see that it goes to the sort of upper detector in our experiment. And similarly, given that the particle was in spin down at some earlier time, then we know that we will get a detection in the lower detector in our experiment. So Griffith says these conditional probabilities tell us that if the measurement outcome is the upper detector at time t2, then we can be certain that the particle had a up spin at t1 and vice versa. And so it is the above conditional probabilities which tells us that what we have been referring to as a measurement process actually deserves that name, for it shows that the result of this process is a correlation between specific outcomes and appropriate properties of the measured system before the measurement took place. So that's the important thing here, is that, like I said, in the sort of orthodox quantum theory, we have this idea of the wave function collapse, and that says that before we took the measurement, there was no way to know what the state of the particle was. It didn't have a definite state. But here they're saying that in a particular framework, so in this case the z direction framework for spin, that when we take a measurement and we get an outcome, then we know that times before that what the actual state of the system was in the z direction. Again, we can't say anything about the x or y direction when we know what the z direction is, but we can say that before the measurement that the system definitely did have, so if we measure it in z spin up, that the system had a spin up in the z direction state even before the measurement. There wasn't any actual collapse of the wave function here. So Hohenberg, in his 2010 paper, says that it should be noted for clarity that the histories of consistent quantum theory are different from the histories in Feynman's path integral formulation of the solution of the Schrödinger equation. In the Feynman case, the histories are associated with complex amplitudes so that they interfere with one another, whereas the histories of consistent quantum theory are mutually exclusive and only appear in terms of their real probabilities in any physical predictions. The mysterious physics of quantum superpositions is fully captured in consistent quantum theory by the existence of multiple incompatible frameworks, each one of which is in a sense classical, not by interference of histories or any other superposition. Hohenberg also goes on to say that the Schrödinger cat paradox can be thought to arise because one is implicitly thinking in terms of the unitary framework and at the same time thinking of the system as containing a superposition of live and dead cats. And so essentially, they're saying that you're trying to use two incompatible frameworks to describe the same thing. And so that's why we get this weirdness here. So according to consistent quantum theory, however, there are no cats at all in the unitary framework, and in the cat framework, there are no superpositions. The simple analog for the spin half system in the state, so the spin up in Z is to say I will accept a superposition of a spin up and spin down in the x direction for microscopic states, since we know from experience that the micro world is weird, but for macroscopic cat states that is impossible. The answer from consistent quantum theory is that in neither case, micro or macro, is the superposition a valid quantum mechanical description. In the Z framework, neither x spin up or x spin down is defined, so no cats. And in the X framework, we have either that the spin is one half, so positive one half, so spin up, or that it is spin down, so alive or dead, each with a probability of half. For the macroscopic case, the analog of the Z framework is the unitary framework, and it has no simple physical interpretation, and certainly no cats. The analog of the X framework is the set of Boolean alternatives, live cat or dead cat, with appropriate probabilities for each. And so it's saying that the weirdness here of the Schrödinger cat paradox just comes from trying to use two incompatible frameworks to describe the entire system. And if you look at Griffith's book on this, he goes through a lot of the different paradoxes trying to show how consistent quantum theory can sort of account for all of them. And I'll actually have his full book linked to in the lecture notes, which will be linked to in the description down below. So his entire book you can find online, and I will have a link to that in the lecture notes if you want to read that. It's actually it's an interesting read, and it kind of goes through, like I said, a lot of the different paradoxes and weirdness in quantum mechanics and tries to show how consistent quantum theory can account for that. But like I said, I feel like it's kind of unsatisfactory because it does essentially just say that, well, when you're, measuring in this framework, then the other frameworks aren't real, and so that's why we get these weird things. But it doesn't really explain how, these weird things come about where, at least in sort of the orthodox quantum theory, where we have, like say in the double slit experiment, the particle is sort of interfering with itself, which, sounds strange and unintuitive, but at least that sort of explains how you get an interference pattern, for instance. And so, because the interference of the particle with itself, you can have the destructive interference and constructive interference, and that explains how you get the interference pattern. Where with the consistent quantum theories, it essentially just sort of waves its hand and says, well, those things aren't real when you're looking at it from that framework, and so that's how you end up with this weirdness. But it doesn't, at least in my mind, explain very well, how these things actually come about. But anyway, here's my sort of summing up of consistent quantum theories. So what it says is there are multiple different possible histories that could have led to the observed result of an experiment. Only the histories that are consistent with an experimental setup can have anything meaningful said about them. So the experimental setup sort of telling us what our framework is going to be, and so that restricts us to a single framework. That's that single framework principle, and so we can't then say anything meaningful about what's going on in other frameworks. So the history that led to the experimental observation is real, meaning that our experimental observation says something that we can know about the state of the system even prior to the measurement. So the measurement apparatus is a part of the system being measured. That's part of the history of the phenomena being measured, and so there is no measurement problem. Again, with the consistent quantum theory, uh, I read through a lot of Griffith's book on this, and he tries to show that there's no measurement problem. He has like 2 full chapters dedicated to the measurement problem. But even after reading it, it just didn't seem like it was all that satisfactory to me. How it's trying to address the measurement problem. But anyway, so any history is not compatible. In other words, they do not commute, or their operators do not commute with the history that led to the observed result, do not exist in any real or knowable sense. So these strange results observed in quantum phenomena occur because of these non-real and non-knowable histories that are incompatible with the experimental observation. So for instance, in the double slit experiment, the particle does not pass through both slits. These strange phenomena observed, interference patterns, because the experimental setup is not compatible with a history of the particle going through either slit. And so if we have a detector here and we end up losing our sort of interference pattern, that's because we are now in a framework that tells us that the particle definitely went through one slit or the other. So we can know, just like we can know, the spin in the z direction, but we don't know the spin in the x direction. And so in this one, where we do get the interference pattern, we're saying that we don't know, which slit it went through, and so that's why we get the interference pattern. But again, like I said, that seems unsatisfactory to me because it doesn't account for why we really get an interference pattern. Why isn't it, some other weird pattern that we get? Why? And they would probably say that it's because, it does still follow the Schrodinger equation, which would predict sort of interference here. But they're saying that, that thing is not actually real in any real sense. And so, it's again to the way that I interpret what Griffiths is saying, and maybe I'm wrong about this, is essentially saying that we don't know what's going on, and it's not even real what's going on there, and that's why we get these weird results from our quantum experiments. But anyway, that was what I wanted to say about consistent quantum theory. Again, Griffiths boasts here that this is supposed to be Copenhagen done right, and so as we saw, this is really taking Bohr's complementarity thing very seriously, but then saying that when we measure something in one of the complementary things, which they call a framework, that is actually a very real measurement, and we can actually say something real about the system prior to that measurement, but we couldn't then say anything meaningful about other frameworks, or as Bohr would call it, other the complementary sort of things with that particular measurement that we took. But anyway, this video has already gone on long enough. I hope you found this interesting, and I will see you in the next one.